China just built a bridge that generates electricity from traffic vibration, and the mechanism is stranger than most engineers expected. Every time a truck rolls across, tiny crystals buried inside the deck get squeezed and release a burst of electricity. Over and over, thousands of times an hour. Thousands of pulses an hour from a material you could hold in one hand. You heard that right. That is roughly the same electrical rhythm as a small power substation ticking away non-stop, hidden inside a road surface. And that is just the beginning, because the crystal itself is not new. What China figured out is how to make it survive under a bridge. Hit a quick like and subscribe so you do not miss the next one, because by the end of this video, you are going to understand exactly how squeezing concrete makes electricity. But first, picture the bridge everyone already trusts. For more than a century, the modern bridge has been one of the most trusted structures human engineering ever produced, and that trust was earned, not assumed. Reinforced concrete and structural steel became the default for a simple reason. They behave predictably under enormous, repeated stress, decade after decade, without asking anything of the world around them. Engineers love reinforced concrete because it is honest, pour it correctly, and it tells you almost exactly how it will behave for the next 75 years. Manufacturers love it because the raw materials, sand, gravel, and steel rebar, are cheap, abundant, and available almost everywhere on the planet. Governments love it because a well-built bridge, once opened, becomes almost invisible in a budget, with no moving parts, no fuel, and nothing to maintain beyond paint and routine inspection. Picture a bridge like a good pair of work boots, unglamorous, boring by design, and precisely because of that, dependable for decades without a second thought. You do not admire work boots for their style. You trust them because they simply do their job, every single day, without complaint. A single major highway bridge in China can carry more than 80,000 vehicles a day, roughly the population of an entire mid-sized American town, crossing back and forth every 24 hours. Multiply that across the more than 1 million bridges currently standing across the country, a network longer than the distance from Beijing to the surface of the moon and partway back, and you start to grasp the sheer physical scale of weight these structures were built to endure. That volume of moving weight is exactly the kind of relentless stress reinforced concrete was engineered to absorb without complaint. And for 100 years, it did its job perfectly. So here is the part that puzzled engineers for decades. If a bridge already absorbs that much mechanical energy every single day, where does all of that energy actually go? The honest answer, for over a century, was that it simply went nowhere, dissipated instantly as heat and vibration the moment it was created. Why didn't anyone try to capture it sooner? Mostly because nobody seriously believed a structure built purely to hold weight could also be redesigned to harvest it. That assumption was reasonable, given everything engineers understood about structural materials at the time. It was also, as it turns out, wrong. Bridges were built to survive force, never to use it. And that quiet, century-old assumption was about to be tested in the most literal way possible. But underneath that century of trust sits a structural blind spot nobody built the industry to solve. Every bridge on Earth is an energy sink, never an energy source, and that gap costs far more than most people realize. Rural and mountainous regions of China have tens of thousands of bridges that carry real heavy traffic but sit far from any power grid, which means the sensors meant to monitor cracking, corrosion, and structural fatigue often cannot run at all. This is not about convenience. It is about structures that can fail silently, with no instruments awake to notice. Installing grid power to a single remote bridge monitoring station can cost more than $80,000, close to the price of a fully outfitted fire engine, just to keep a handful of sensors and a warning light alive. Nationally, transportation researchers have estimated that more than 60,000 rural and mountain bridges sit essentially unmonitored, a blind spot spanning a road network longer than the entire United States interstate system, stretched twice over. The consequence is not abstract. Between 2000 and 2018, structural failures linked to undetected fatigue damage on unmonitored rural bridges in China contributed to dozens of closures, each one cutting off villages from hospitals, schools, and markets, sometimes for months at a time, while inspectors traveled in on foot. Here is the brutal catch. The very mechanical force threatening a bridge's long-term structural health was also the one resource sitting right there, completely unused, every single day. Millions of tons of vehicles rolled across these structures constantly, and every ton of that force disappeared into the concrete as wasted heat and vibration, gone before anyone could measure it. It was mechanical energy equivalent to dozens of small wind turbines spinning quietly under the roadway, every single day, with absolutely nothing built to catch it. What if the bridge itself could power its own eyes, without a single wire running back to the grid? That question sat unanswered for years, mostly dismissed as impractical by engineers focused on strength, not electricity. Running a diesel generator to each of those sites was another option on paper, but the fuel cost alone made it a non-starter for a government managing tens of thousands of similar structures at once. In 2019, engineering teams at Southeast University in Nanjing began answering that question with data that was harder to dismiss than anything the field had seen before. The team credited with cracking this problem worked out of Southeast University in Nanjing, alongside materials researchers from the Chinese Academy of Sciences and engineers from China Merchants Chongqing Communications Technology. The core idea sounds almost too simple once you hear it. Certain crystals, when you squeeze them, produce a tiny electrical charge, a property called the piezoelectric effect that scientists have understood since the 1880s. Previous attempts to use this effect in roads and bridges failed for one consistent reason. The crystals that generate the strongest charge are also brittle, and a bridge deck crushes anything brittle within months under real truck traffic. Earlier prototypes in Europe and Japan cracked apart after roughly 6 months of highway use, generating a promising trickle of electricity right up until the moment they physically disintegrated. Researchers at those earlier labs had already proven the concept worked in principle. What they never solved was survival, and that gap sat unresolved in engineering journals for the better part of 2 decades. Here is the part that puzzled the field for years. The better a material was at generating power, the faster it destroyed itself. Think of it like a wine glass that sings beautifully when you run a finger around the rim, but shatters the instant you set something heavy on top of it. The Nanjing team's breakthrough was not a new crystal at all. It was a flexible composite casing, layering the piezoelectric crystals inside a polymer matrix that flexes instead of cracking under repeated compression. Now, here is what makes this genuinely different. The casing lets the crystal deform slightly under each truck's weight and spring back completely, thousands of times an hour, the way a running shoe's sole compresses and rebounds with every step without ever losing its shape. In laboratory fatigue testing, the encased material survived more than 10 million compression cycles, roughly equivalent to 15 years of continuous highway traffic, compressed into a matter of months, without a single unit failing structurally. That single design change was the difference between a science fair curiosity and something you could actually pour into a bridge deck. It also meant the material could be manufactured in flat sheets, roughly the thickness of a dinner plate, thin enough to embed directly beneath the asphalt without altering the bridge's structural design at all. The lab numbers were extraordinary. The only question left was whether real traffic would agree. Start with the limitation, because it is real and worth stating plainly before anything else. A single square yard of this piezoelectric composite generates only a small amount of electricity per vehicle pass, measured in a handful of watt-hours, nowhere close to powering an entire home on its own. But here is what that number actually means in practice. A remote bridge sensor network, the kind meant to watch for cracking and corrosion, needs only a tiny trickle of continuous power to stay awake, typically less than what a single household light bulb consumes in an hour. Anchored against real traffic volume, 80,000 vehicle crossings a day generates more than enough of that trickle, with surplus left over to store in a small battery for cloudy days or overnight lulls. Put another way, the limitation only matters if you expected the bridge to power a neighborhood. Nobody serious ever claimed that. The goal from day one was self-sufficient monitoring, and on that measure, the technology clears the bar with room to spare. Here is the unexpected advantage. Nobody predicted going in. The material also acts as a built-in stress sensor, meaning the same panels generating electricity are simultaneously measuring the exact load and vibration pattern passing over them in real time, without a separate sensor network at all. That combination, power generation and structural monitoring in a single material layer, does not exist anywhere else in bridge engineering today. Traditional sensor networks require separate wiring, separate batteries, and separate maintenance contracts, each one a point of failure. Collapsing all of that into one embedded material is the part most engineers did not see coming. Now, here is where it already wins outright. Remote mountain bridges in Yunnan and Guizhou provinces, places where running grid power costs more than the bridge itself was worth, have adopted the technology specifically because it eliminates an entire category of infrastructure cost, not because of the electricity generated. A non-obvious application followed almost immediately. Highway authorities began eyeing the same material for tunnel entrances and way stations, locations where power access is limited, but vibration is constant and predictable. The question was no longer whether piezoelectric bridge decking worked. The question was how quickly it could be scaled beyond a handful of pilot sites. And scaling it meant leaving the careful conditions of the laboratory behind entirely, for the far less forgiving, far messier world of actual highway traffic. In 2022, the technology left the laboratory for good when it was embedded into a 200-yard span of the Wulong River Bridge in Chongqing. Operated jointly by regional transportation authorities and China merchants, Chongqing Communications Technology. Within the first year of live traffic, the embedded panels generated enough continuous electricity to power the bridge's entire structural monitoring network, its warning lighting, and a backup reserve, all without a single connection to the regional grid. The field matched the forecast. That single sentence mattered more in this industry than almost anything printed in a lab report, because bridge engineering has a long history of laboratory darlings that failed the moment real trucks, real weather, and real neglect got involved. Field validation carries more weight than lab data here, specifically because bridges cannot be replaced if they fail. They have to work the first time, in the rain, in the heat, and in the cold, for decades without interruption. A laboratory can simulate 10 million compression cycles in a controlled chamber. It cannot simulate a summer heat wave followed immediately by a hard freeze, or the constant low-grade humidity of a river valley in monsoon season. And the Chongqing site delivered exactly that kind of unforgiving environmental stress test. One detail mattered as much as the electricity generation itself. The panels could be installed using the same paving equipment already used for standard asphalt resurfacing, requiring no specialized machinery and no extended road closures beyond a normal repaving schedule. Compare that to early European pilots, which required custom embedding rigs and closed entire lanes for weeks. And the manufacturing compatibility alone explains why this pilot scaled, while others quietly stalled. The performance data itself has been logged on China's National Transportation Open Data Platform since the pilot began. allowing outside researchers to verify the numbers independently rather than taking the operator's word for it. As one senior bridge engineer involved in the pilot put it, "We stopped thinking about this as new technology the day our own paving crew installed it without any additional training." If a bridge generating its own power from traffic surprised you, the next part is going to be even harder to believe. Hit subscribe so you're there when we cover it. It started with one application where remote monitoring mattered more than raw electricity output. Then, it spread outward from there to tunnels, way stations, and toll plazas across 4 provinces. The claim now had receipts. More than 140 international patent families now cite the core piezoelectric embedding technique pioneered at Southeast University. These are not academic citations. These are legal and financial commitments, each one representing a company betting real money that this specific approach is worth defending. China merchants. Chongqing Communications Technology has committed more than $40 million to a 5-year rollout across mountain highway networks in 3 provinces, an amount roughly equal to the cost of building 4 new rural bridges from scratch. Huawei's Smart Infrastructure Division has separately confirmed a research partnership exploring the material for embedded sensor arrays along its planned smart highway corridors. In Germany, Fraunhofer Institute researchers announced in 2023 that they were testing a licensed variant of the composite casing on a pedestrian bridge outside Stuttgart, marking the first confirmed Western deployment of the underlying design. In the United States, a small transportation technology firm in Colorado has filed for a testing permit to trial a similar embedded system beneath a rural highway bridge, though full deployment there remains at least 2 years out. China's Ministry of Transport has also folded self-powered structural monitoring into its National Bridge Safety Code revisions, effectively requiring new remote area bridges to include some form of independent power generation by 2027. Here is what that regulatory shift actually does. It turns a promising pilot technology into a mandatory line item on thousands of future construction contracts, almost overnight, rather than an optional upgrade that individual contractors could quietly skip. Regional transportation bureaus in Yunnan, Guizhou, and Sichuan have already begun updating procurement specifications ahead of the 2027 deadline, well before the national code even takes formal effect. In any market where installing grid power costs $80,000 per site and a self-powered alternative costs a fraction of that, a large cost advantage is not a trend. It is a competitive pressure no serious contractor can afford to ignore. Now, here is the detail that puts everything into perspective. None of this depends on a single company succeeding. The underlying patents are now licensed to manufacturers across 4 countries, meaning the technology's future no longer rests on one team's continued success or on the fortunes of any single government contract. All of the pilot performance data referenced here remains publicly logged on China's National Transportation Open Data Platform, available for any independent researcher to verify directly, rather than take an industry press release at its word. If this approach were applied across even a quarter of China's remote and mountain bridges, industry estimates suggest it could eliminate the need for grid extension to more than 15,000 individual sites, a combined stretch of infrastructure roughly equivalent to wiring every small town in California for power from scratch. The secondary benefit runs alongside the primary one. Each avoided grid extension prevents an estimated 60 tons of carbon emissions tied to cable manufacturing, trenching equipment, and transport, meaning wide adoption could avoid emissions comparable to taking 20,000 cars off the road for a year. But turning a promising technology into a global standard is a long road, and it is important to be honest about where that road gets genuinely difficult. The composite material currently costs roughly 30% more per square yard than standard asphalt paving. a premium that only pays for itself over 5 to 7 years of avoided grid and maintenance costs. Manufacturing capacity remains concentrated in a handful of facilities in Jiangsu province, creating a bottleneck if rollout demand accelerates faster than production can scale. A constraint that echoes the early growing pains of most new construction materials before supply chains mature. Long-term performance data beyond 5 years does not yet exist, since the technology itself is barely half a decade old in real-world deployment. Cold climate performance above the Arctic Circle equivalent latitudes remains untested, and freeze-thaw cycling could behave differently than the temperate conditions studied so far. Regulatory approval outside China remains slow, with most Western transportation authorities still treating the material as experimental rather than standard, a classification that can add years to any approval timeline, regardless of how strong the underlying data looks. And skilled installation crews familiar with the embedding process remain concentrated almost entirely within China, meaning international projects will need training pipelines built essentially from scratch. Here is the part most people miss. None of these are reasons to doubt the science. They are reasons the rollout will take years, not months. None of these challenges change what the science shows is possible. They define the gap between what is technically achievable and what will actually happen at scale. Closing that gap is an investment problem, a policy problem, and a coordination problem as much as an engineering one. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the infrastructure transition demands is a different question entirely. The story of self-powered infrastructure is ultimately the story of what human civilization can build and where it can build it. For most of modern history, remote and mountainous regions were left out of the digital safety net simply because running power to them cost more than anyone could justify. This technology inverts that logic entirely. The places with the least access to grid infrastructure, mountain communities in Yunnan, rural stretches of Guizhou, isolated river crossings across the interior, are precisely the places that benefit most, because the bridge itself becomes the power source. That access gap has existed for decades, and closing it will not happen overnight, but the direction of travel is now honest and clear, tilting toward the communities that infrastructure planners overlooked for generations. What is genuinely new here, not incrementally better, but categorically different, is a structural material that simultaneously bears load, monitors its own health, and generates its own power, with no external input required at all. That is not a minor improvement. It is a different category of solution, one that treats a bridge as an active system rather than a passive object. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the infrastructure transition demands is a separate question, one that belongs to policymakers, investors, and manufacturers as much as it belongs to scientists. That is new. And scale is exactly why this matters more than one bridge in Chongqing. China alone maintains more than 1 million bridges, and every one of them experiences the same daily waste of mechanical energy this technology now captures, which means small efficiency gains here compound into enormous ones as adoption spreads nationwide over the coming decade. If a bridge quietly generating its own electricity raises a question about what other everyday materials are hiding untapped potential, that story is worth understanding too, and it is the subject of our next video. China's new material just replaced wood forever. The link is in the description. If this changed how you think about the bridges you drive over every day, hit that like button and subscribe so you never miss what comes next. Turn on notifications. We publish every 2 weeks. Now I want to hear from you in the comments. Should governments mandate self-powered infrastructure like this, even when it costs more upfront? Or should the free market decide when the technology is ready?